So we recall, atom stability is all about having 8 valence electrons. If we don't have 8 valence electrons, hey, we're going to gain electrons so that we can have 8. Or, as we're going to see in this video, atoms can lose electrons in order to have 8. Let's take a look at magnesium. So magnesium's electron configuration. Let's zoom over to that periodic table. Here's magnesium. You want to write the electron configuration for magnesium, always starting here with hydrogen, as we know. It's going to have an electron configuration of 1s2, 2s2, 2p6, 3s2. If you need a refresher of electron configuration or need some more assistance, please refer to your notes and the videos from previous lessons. From the electron configuration, I can determine the number of valence electrons. Look for the biggest coefficient. It's the number 3. The third energy level is the highest occupied, so the number of valence electrons is going to be 2 valence electrons. Magnesium is not stable because it has only 2 valence electrons. Remember, the perfect number is 8. Let's take a look at the orbital notation. Magnesium's orbital notation would look like this. 1s with 2 electrons. You got 2s with 2 electrons as well. You got 2p with 6 electrons total. And look at the way I will fill this in. Up, 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 down, down, down. And then finally, you got 3s that also has 2 electrons. Tell me, how many valence electrons are present? I use the same logic as I did with electron configuration. Find the biggest coefficient. And now it's literally counting the number of valence electrons represented as arrows. They're going to be these guys right here in the 3s. That's 2 valence electrons. So either way you look at it, magnesium has 2 valence electrons, so it's not going to be stable. It is highly reactive. Well, how can magnesium then become stable? How can it have its 8 valence electrons? You might say, hey, well, if it has 2, it just needs 6 more to have 8 valence electrons. And then it obeys the octet rule. But there's something actually a little bit easier here. What if magnesium lost those 2 valence electrons? These 2 right here in the 3s orbital, what if it just got rid of them? Let's lose. What happens if Mg loses or lost those 2 electrons in 3s? So imagine that 3s is not there. Guys, what's left over? If 3s isn't there, then look here. Energy level now. The second energy level is the highest occupied energy level. And now count for me. Count how many valence electrons are in the second energy level. You got 2 in 2s. You got 6 in 2p. Add them together. You now have 8 valence electrons. Just by getting rid of those 2 valence electrons inside of 3s. So let's clean this up a bit. I get rid of 2 valence electrons in the 3s in this orbital notation picture. Let's also get rid of those 2 electrons here in the electron configuration. We'll do the same thing. Okay, we got to make sure that the electron configuration matches our orbital notation now. Let's rewrite this because it's gotten a little messy. rewrite your electron configuration, rewrite the orbital notation to become stable, aka have 8 valence electrons. All magnesium needs to do is lose 2 electrons. The resulting electron configuration is, I'm sorry, not the electron configuration, the orbital notation. Let's draw that first. The resulting orbital notation after magnesium has lost its 2 valence electrons is now this. Let's write the electron configuration for that orbital notation. It's a 1s2, 2s2, and 2p6 configuration. Both of these say the same thing. Both of these are saying magnesium now has 8 valence electrons. And that is the result after magnesium loses 2 electrons. Now, Mg is stable with its 8 valence electrons. But just as we did when we gained electrons, when we lose electrons, we're no longer neutral. Magnesium is no longer a neutral atom. So I gotta figure out, what's the charge of this magnesium ion that we've just created? Well, it lost 2 electrons. Let's think about this. If magnesium starts, it's number 12. That means 12 protons. And let's count how many electrons are in our picture in our orbital notation. I count 10 arrows. Now it has 10 electrons. And think about that. If it started with 12 electrons in its neutral state, and we just said it lost 2 electrons, 12 minus 2 is 10 electrons. And so based off of this information, can't we say then that the symbol is going to be magnesium 2 positive? Because there's 2 more protons than there are electrons. So this is really the orbital notation for magnesium 2 plus ion and the electron configuration for the magnesium 2 plus ion. So in summary, guys, atoms can either be stable or unstable. Those that have 8 valence electrons are stable. Those that do not are unstable. And it's those unstable atoms that are going to gain or lose electrons. The result of gaining or losing electrons are ions. And remember, that's all just atoms with charges. So how do you know if an atom gains or loses electrons? Make it real simple. Atoms with 5 valence electrons or more gain electrons. So that they're going to have 8. Okay, they're going to gain electrons to have their 8 valence electrons. The result of gaining electrons is that these atoms are going to turn into they're going to turn into negative ions. Negative ions. And in chemistry, we give these negative ions a fancy chemistry name. These are called anions. One important thing to note, when I say atoms with 5 valence electrons or more, if it has 8, remember that's already a stable atom. It's not going to gain electrons. Okay, so really I'm saying 5 valence, 6 valence, or 7 valence electrons. And so that means all other atoms with less than 5 are going to lose electrons. When they lose electrons, the result, positive ions. And again, in chemistry, we like to give things names. Fancy chemistry name for positive ions. They're called cations. Okay, so you got 2 new vocab words here, anions and cations. The word cat, I like to tell students, hey, look at that word cat. It has the letter T in it. Think cat, T, T plus sign, positive sign. So your cations are going to be your positive ions.